gravity. Now, you all know that Sir Isaac Newton was the first to come up with a good mathematical treatment of gravity. And he did this in his seminal work, the Principia Mathematica. The full title is Philosophiae Naturalis Principia Mathematica, which is to call it the mathematical principles of natural philosophy, which is the mathematics of physics, right? Um, Now, he didn't really think it would ever come to anything. He just really enjoyed doing it. It was kind of stuff he enjoyed doing. He did physics problems and solved hard problems all the time just for fun. Um, but since he didn't think it was anything that would ever come to anything, he actually took a post with the crown in the Royal Mint, and he invented the little ridges around the edges of coins, like a quarter or a dime. And those ridges were there so that people couldn't trim a little bit of silver off of them and sell the silver separately from the coin and have the value of the coin hold up. This was an enormous problem back in the late 1600s. Um, Contemporary to Newton is another physicist nobody ever really hears about, Gabrielle Amélie Letonne de Bretuel, Marquis de Châtelet. She was a mathematician and physicist, but she was a woman, so she never got to go to school. She couldn't go to school. She couldn't go to university, and she was taught to read and write as a matter of course because she was royalty. But she was curious. She was excited about learning, and so she would actually just hang out in the halls at the university, and she learned mathematics and science and physics just hanging out in the halls and listening to the lectures that were happening while she hung out in the halls. Well, her big thing that she did that nobody knew about for the longest time was she took Newton's Principia, which was in Latin, and translated it into French. Not only did she translate it into French, she started cleaning it up and fixing some of his mistakes that he made. So here's Newton. He invents calculus in order to explain the physical world. No one has ever seen calculus before. Here's Amélie Marquis de Châtelet. She picks up the Principia. She learns the calculus. She learns it well enough to fix some of Newton's problems, and she writes this translation and her appendix to it and shoves it in her drawer, in drawer of like her makeup cabinet or something like that, or her desk where she sat and worked all the time, and no one knew about it because she died in childbirth. Right? She's quite young when she dies, in her early 40s, quite old to be trying to have a child. There's a lot of upset about that, but she died. She died in childbirth. 9 years later, someone opens her desk door and finds her translation of Newton's Principia. That translation is still the official French translation today. All right, so Newton, Amélie Marquis de Châtelet, two important figures, one you know about, one you don't, in the world of physics in the 1700s, early 1700s. One of the things in there is gravity. Now, you've heard about gravity all your life. Because you've heard about it, you have a leg up in terms of realizing it's even there, right? Because for most people, realizing that there's something there that we can model and call gravity is a big step if you haven't heard of it before. So here we are. Newton, in some sense, discovers gravity, provides a mathematical treatment for it. Gravity causes things to be accelerated, right? And the acceleration of gravity here at the surface of the Earth is about 9.8 meters per second squared. We have to keep in mind, if we call up positive, that means the acceleration of gravity is minus 9.8 meters per second squared. If we call down positive, then we can call that a positive 9.8, but typically we call up the positive direction. You'll also notice I wrote this as g. That's what we use as a symbol for the acceleration of gravity all the time. Minus g, when we put it in the context of positive is up, then the acceleration of gravity is minus g. G is just the scalar, 9.8 meters per second squared. You have to take care of the vector part, which is this sign, yourself. Okay. So if we look at this acceleration of gravity, well, what equations are we going to use? It's really nothing other than our constant acceleration equations right here, right? We're going to use those equations. We're just sticking in, instead of x, which we typically think of as horizontal, we're sticking in y, which is what we usually use for vertical. All right? We use y to describe the vertical direction. We often use x to describe the horizontal direction. So if we look at this picture, we have some initial position y naught, right, which we're going to call 0, at time t naught, which we're going to call 0, and we have an initial velocity up of 13 meters per second. Since we're calling up positive, that means we have initial acceleration down of minus 9.8 meters per second squared. So if we stick this into our equation for y is minus 1/2 times 9.8 meters per second squared times time squared plus 13 meters per second times time plus 0 meters. So here is our acceleration, minus 9.8 meters per second squared, the 1/2, the t squared. Here's our initial velocity, 13 meters per second, times time. Here's our initial position, 0 meters. In part B of the picture, instead of throwing it up, we're going to throw it down, right? The only thing that changes is the sign on the initial velocity. The initial velocity is now down or negative, right? So part A, throwing up, part B, throwing down, all right? All looks pretty good in terms of, yeah, we've got our equations, we've got it set. We can solve now at any point in time what is the position of the ball that this guy is throwing, what is the position of the ball vertically at any point in time using these equations under these two different initial conditions. All right, that's it for the part on gravity.